And I think in this particular short talk, I will briefly summarize the accomplishments of the Induced Seismicity Research Project for the year of 2020 to 2021. Okay. So this is the abstract of this talk. Because this talk, as Gio indicated, that it will be recorded and be made available later, so I will not repeat all the statements here. In the next 15 minutes also, I will focus mainly on these 4 items that I consider as key accomplishment during this year. The first one is the adaptation of research results into the regulatory framework of induced seismicity earthquake in BC, and the publication of research results on source characteristics of significant induced earthquakes in Canada, and the development of innovative methodologies for detection and location of repeating earthquakes and precise earthquake focal depths, and finally, the enhanced injection-induced earthquake catalog and monitoring for major shale gas basins in BC and Alberta. This slide is a list of project members that include the scientists and supporting staff from 3 GSC offices at Sydney, Ottawa, and Quebec City. We also have worked very closely with colleagues, and that's supported by external fundings from various organizations, including Geoscience BC and the BC Oil and Gas Commission, universities, and so on. Before I present our scientific research results, I'd like to first acknowledge a few recognition and collaboration highlights of our research. First is the publication leading to regulatory changes, and specifically BC Oil and Gas Commission announced earlier this year through their Industry Bulletin 2021-05 that their regulatory decisions on induced earthquakes in BC will be made according to the magnitude values calculated with the formula that we established earlier in 2018 and then updated in 2020. We also have leveraged a significant amount of research resources through collaboration with other organizations, and BC, Geoscience BC gave us a grant of more than $154,000 to support the routine operation of seismograph stations and induced seismicity research in Northeast BC. And we also have more than $135,000 contributed by the BC Seismic Research Consortium in support of our research. We have established a very close working relationship with many universities and Geoscience BC and BC Oil and Gas Commission, as well as the Canadian Association of Petroleum Producers, to densify the local and regional seismograph coverage in both BC and Alberta. And finally, we have published many publications internally and externally with our collaborators. So this is a slide that summarizes our study to improve the magnitude calculation for earthquakes that occurred in Western Canada. In the top figure here, it shows the magnitude values for 3 different earthquakes, represented by 3 different symbols. And each of these symbols represent 1 magnitude value calculated at one station from using data from one station. And it becomes very clear that when the stations are located more than 100 kilometers away from the epicenter, then the value becomes systematically higher. And this actually creates a very confusing situation for the industry as well as the regulator, because the industry quite often have their own seismic network, and their stations are located very close to the earthquake epicenter, and therefore this is the magnitude values that they derive. Whereas the regulator depends on the reported value by the NRK network, which quite often located far away from the epicenter. So the NRK reported magnitude systematically becomes larger than the industry-derived value. And that actually make the regulatory decision very difficult. So the purpose of this particular study is to derive a new formula that can be used specifically for Western Canadian earthquakes so that we can eliminate this discrepancy. Now, I won't be able to describe the detail, but this is the formula that eventually we derived, which has a nice attenuation correction for the magnitude calculation with respect to depths, distance. So the end result is shown here, that you can actually get a very nice consistent magnitude value from about 2 kilometers away from the epicenter all the way to hundreds of kilometers away. And therefore, this formula will make the value very consistent, doesn't matter which network you are using. So this is the basic reason why the BC Oil and Gas Commission decided to adapt this formula in their regulatory decision process. Okay, and this is a slide that describes a case study of the mine blasting events in central BC. We actually observed a series of earthquakes that occurred in the vicinity of a blasting site here. And this is a regional map. Here is the BC, this is Alberta, and that's the location of the blasting sites. And we observed this series of earthquakes that actually form a linear feature along this part of the central BC. And in order to determine the relationship between these events and the blasting activity, we developed a multivariate decision tree, which is shown here. Eventually, what we have found is that many of these observed earthquakes that are carefully relocated, as shown on this map, that can align very remarkably well with the Rocky Mountain Trench, which is this feature to the south of it. And this actually suggests that perhaps these events actually represent a reactivated part of a unmapped fault system in that region. So the underlying implication of our study is that the seismic hazard can be very significant if this entire 150 kilometer segment ruptured at the same time during a major earthquake, which will equivalent to a magnitude somewhere around 6 to 7, and that can be very hazardous to the region. This is a study that focus on the strain accumulation and the strain release rate in Canada and northern United States. Specifically, we collect the GNSS data, which is formerly known as the GPS, and to use the GNSS data to calculate the ground motion at all the GNSS stations. Now, from these motion vectors, we derive the horizontal strain rate, as well as their deformation mode that describe if the deformation is in contraction or in extension. Now, from this horizontal strain rate, we were able to calculate the strain accumulation rate. Now, on the other side, we collect seismic data and calculate the seismic moment that's released by all these earthquakes. And these seismic moments are then converted to seismic moment rate, which represent the release of this strain accumulated by the tectonic force. And on the right-hand side, we compare the strain accumulation versus strain release rate, and this is the ratio. What we found is that the less than 20% of the tectonic energy actually is released by seismic activity. And most of the differences between the aseismic and seismic deformation can be explained very well by the glacier isostatic adjustment, especially for Eastern Canada here. And we also, based on this ratio distribution, we estimate the recurrence interval for major earthquakes that actually varied quite a bit from decades along the plate margin area in the West to thousands of years in the stable continental interior. And here is a slide that shows an example of our case studies of the source processes of hydraulic fracturing induced earthquakes in Western Canada. Now, this is a map of our study area, which is a zoom up part of the BC and Alberta. And in this particular study that I'm showing here, we zoom in to this area where we have 3 active hydraulic fracturing injection wells. And this lower part is the injection activity shown by these color shades. And the bars represent the number of earthquakes. As you can see, the first series of earthquakes actually happened about 5 days later from the onset of the injection, whereas the second and then the third sequence of earthquakes have almost no delay. So the detailed analysis of this spatial temporal distribution of earthquakes versus injection, and also the results of simulation suggests that, well, first of all, the largest hydraulic fracturing events appears to have a stress drop value that's very comparable to that of tectonic events, which is in the range of 1 to 35 megapascal. And based on their spatial temporal distribution, we conclude that it is very likely that the main shock of this sequence, the first sequence, is caused by the migration of injected fluid. And this is also reasonable that can explain the 5-day delay from the onset of the earthquake to the from the onset of injection to the earthquake. And if you look at this map here, we also observe that many of these smaller events appears to have many of these events that's closer to the injection sites appears to have lower stress drop comparing to those that appears to be farther away from it. So the interpretation is that these closer events nearby the injection well probably represent the higher fracture density and elevated pole pressure in the rock matrix, and therefore their stress drop is lower. We actually have also developed new methodologies to improve the resolution of our analysis. And one new method is presented here. And this is what we call the the match filtering with multi-segment cross-correlation, MFMC. In the middle part, this is the mathematical expression of this method, and I certainly have no time to go into detail of it. But I like to show 2 examples to demonstrate the advantage of this method with respect to the conventional approach. Now, on the left-hand side, we select 2 events that are not repeating earthquakes. So if you look at the waveform, they look very similar to each other. However, if you examine the detail of their coda part, there are some discrepancies, especially here and there. And obviously, they indicate that these 2 events are not repeating events. On the right-hand side, I'm showing you 2 other examples of earthquakes, and they have 2 identical waveforms. You can see that their waveforms are really identical. So using the old approach, both right-hand side and left-hand side events give you very high cross correlation value. They are all higher than 0.9, which is extremely high. And therefore, in the old approach, both are considered repeating events. But if you look at the, if you use our new methods, the left-hand side give you a cross-correlation value much smaller than 0.9, whereas on the right-hand side, it is as good as the old one. So our method can successfully distinguish whether or not these are true repeating events or not. Another method that I would like to introduce is what we call the depth scanning algorithm. And this algorithm, basically take advantage of the depth phases that is very sensitive to the focal depths using reflected phases. And again, I have no time to go to the detail, but on the right-hand side, you can see by using this method, we were able to actually identify the depths very nicely using a true earthquake example that happens in South Carolina, where two studies actually indicate that they have different solutions. And our study suggests that the shallower solution appears to be the good one. And the USGS solution perhaps is too deep. So finally, this is a map showing our catalog for the past 2 years that in comparison with the Canadian National Earthquake datasets, we have we're putting a lot of efforts trying to make a comprehensive induced earthquake catalog that can be useful for both the industry and the regulator. As you can see, the number of earthquakes that we located are way more than the routinely reported one. So this is a list of the key publications that I just described, and you are very welcome to check them out. If you want to reach me, this is my contact information, and thank you for your attention.